Black holes are among the most fascinating objects in our universe, and also the most mysterious.
From antiquity, it was believed that the idea of empty space is a conceptual impossibility. Space is nothing but an abstraction we use to compare different arrangements of the objects. Concerning time, it was believed that there can be no lapse of time without change occurring somewhere. Time is merely a measure of cycles of change within the world. Then, in 1686, Isaac Newton founded classical mechanics on the view that space is real and distinct from objects, and that time is real and passes uniformly without regard to whether anything moves in the world. He spoke of absolute space and absolute time as a stage within which matter existed and moved as time flowed at a constant rate. It was understood that space and time tell matter how to move, but matter has no effect on space and time. The idea that space and time act on matter, but that matter does not act on space and time, troubled Einstein. Noting that light curved in a gravitational field, Einstein proposed that the mass of an object does indeed act on the space and time it exists in. Specifically, he proposed that the presence of matter curves spacetime. This led Einstein to his theory of general relativity, which predicts the existence of black holes as objects so massive that light itself cannot escape their gravity. You'll recall explosions at the end of life for stars less than 5 times the mass of the Sun leave behind a white dwarf. In these stars, electron exclusion pressure is enough to counteract the inward force of gravity. Supernova explosions at the end of life of stars more than 5 times the mass of the Sun leave behind a neutron star. In these stars, electron exclusion pressure is insufficient to overcome the force of gravity, but neutron exclusion pressure is. But if a star is greater than 30 times the mass of the Sun, even neutron exclusion pressure won't do the trick. In fact, there is no known force that will counteract the inward force of gravity for such a supernova or hypernova exploding star. According to Albert Einstein's general theory of relativity, the star will collapse into zero volume and infinite density. This is called a singularity. This defines a black hole. It gets its name from the fact that such a singularity would create a gravitational pull that not even light could escape. The object literally becomes invisible. In 1916, Karl Schwarzschild, contemporary of Einstein, solved his equation for the special case of a non-rotating sphere. He found that although the diameter of the singularity is 0, the radius at which light would be captured depends entirely on the mass of the black hole. This is called the Schwarzschild radius, and it defines the event horizon. But it would be the rare black hole that doesn't spin. In 1963, Roy Kerr developed a general solution for spinning black holes. It showed that there is a second region beyond the event horizon that defines a volume around the black hole called the ergosphere. In this region, space itself is dragged around by the black hole's spin. It's called frame dragging. Also in this region, light can enter stable orbits around the black hole. This would produce a photon spherical shell encasing the black hole with the light from all the stars in the universe accumulated over the entire age of the black hole. It would be a sight to see.
Scientists have theorized several different types of black holes, with stellar and supermassive black holes being the most common. Stellar black holes form when massive stars die and collapse. They're roughly 10 to 20 times the mass of our Sun and scattered throughout the universe.
One of the things all rotating black holes have in common, besides the fact that we can't see them, is that matter flows in via an accretion disk. The exact mechanism is not yet fully understood, but we know that gamma-ray jets shoot out at the poles, carrying a percentage of the falling matter with it, at speeds approaching the speed of light. In late 2018, ESO's gravity instrument observed flares of infrared radiation coming from the accretion disk around Sgr A. These flares came from clumps of gas swirling around at about 30% of the speed of light on a circular orbit just outside the event horizon. They indicate that Sgr A is spinning with a full rotation every 11.5 minutes. This makes the 4 million solar mass Sgr A star a supermassive Kerr black hole. This new information also enabled calculating the distance from Sgr A star's center to its event horizon at around 10 million kilometers, or 15 times the radius of our Sun, and the distance to the photon sphere at around 17 million kilometers. To illustrate how a black hole might look, we'll build Sgr A star. Here we are viewing it from the equatorial plane, and the object is rotating in on the left and out on the right. Its center is dark out to the event horizon. This thin ring around the black hole, just outside the event horizon, represents the cross-section of Sgr A star's ergosphere, with a shell of orbiting light. What we'd see is the light that leaks out in our direction. The observed flares indicate that Sgr A star has the remnants of an accretion disk that is no longer feeding the black hole on a regular basis. The massive amount of light rays emitted from the disk's top face travel up and over the black hole, and light rays emitted from the disk's bottom face travel down and under the black hole. This combination gives us the full image of how the black hole would actually look. There are 3 classifications for black holes based on their mass: stellar, with masses up to 10 times the mass of our Sun; supermassive, with millions or even billions of times the mass of our Sun; and intermediate, with masses somewhere in between. Sgr A star is a supermassive black hole. In March 2018, the Japanese instrument MAXI aboard the International Space Station recorded an extremely strong X-ray outburst. NASA's NICER neutron star instrument, also on the space station, focused on the outburst for days and watched it fade. In addition, the Gaia mission was able to locate the X-ray source companion star and determine its distance at 10,000 light-years. Analysis showed that the X-ray object is a black hole with a mass of around 10 suns. The X-rays are generated as matter from the star feeds the accretion disk around the black hole. Some astronomers calculate that there are as many as 100 million stellar mass black holes like this one in our galaxy. Most of these are invisible to us, and only about a dozen have been identified. For more information on black holes, see the General Relativity Effects segment of the How Fast Is It video book.
There could be millions of these stellar black holes in the Milky Way alone. Supermassive black holes are giants by comparison, measuring millions, even billions of times more massive than our Sun. Scientists can only guess how they form, but we do know they exist at the center of just about every large galaxy, including our own. Sagittarius A, the supermassive black hole at the center of the Milky Way, has a mass of roughly 4 million suns and has a diameter about the distance between the Earth and our Sun. Because black holes are invisible, the only way for scientists to detect and study them is to observe their effect on nearby matter. This includes accretion disks, a disk of particles that form when gases and dust fall toward a black hole, and quasars, jets of particles that blast out of supermassive black holes.